Grain drying is a proven effective process that is critical for food availability and security, but it comes with a carbon cost that burdens the agricultural industry. The problem with decarbonizing the grain drying process isn't only efficiency, but also economics. It is expensive and farmers won't adopt it unless the numbers work. I am registrar number 273 and will be presenting a self-financing propane pyrolysis retrofit that has the potential to decarbonize the grain drying process. The PPGD project explores a more sustainable alternative to the conventional grain drying process. Instead of burning propane directly, it is first thermally decomposed into a hydrogen-rich gas and solid carbon. This is the key difference. In conventional combustion, the carbon oxidizes to CO2 and escapes. In pyrolysis, the carbon stays solid and can be recovered. The hydrogen-rich gas is then used to provide heat for grain drying, while the solid carbon becomes a potential value-added co-product. To evaluate this concept, I developed both the conventional grain drying and the PPGD processes in Aspen Plus. The conventional grain dryer is modeled to represent the BCT 10,000 commercial tower grain dryer, which has a burner capacity of about 17 megawatts. So here, this process burns propane in excess air to generate the hot flue gas needed to supply the required thermal energy of 17 megawatts for grain drying. This process is carbon intensive, producing almost 4,000 kilograms per hour of CO2 emissions. The PPGD process begins with the propane feed stream, which is conditioned and sent to the pyrolysis section for thermal cracking. The products are then cooled and separated, allowing solid carbon to be recovered and the hydrogen-rich gas to be routed to the grain drying system. A key requirement was that the modified system must still meet the same drying duty as the conventional process. To achieve that, I used Aspen Plus design specifications to automatically adjust the propane feed until the target drying duty was satisfied. I also used calculator blocks to define flow relationships in the combustion and drying section, and sensitivity analysis to study the effect of operating changes on process performance. The Aspen output, including propane requirements, stream compositions, carbon production, and energy flows, were then used as the foundation for the technical and economic evaluation of the system. Compared with the conventional process, the PPGD system creates a clear pathway to reduce direct CO2 emissions by up to 100% at full propane conversion when paired with renewable sourced electricity. That means the carbon that would have gone up the stack as CO2 is instead captured as solid carbon black, a product, not a pollutant. The economics are just as compelling. At full propane conversion and a carbon black price of $2 per kilogram, the system delivers an NPV of $43 million and an IRR of 34%, more than 3 times the discount rate of 10% which was used. And this isn't a narrow result. The sensitivity analysis across propane conversion rates from 20 to 100% and carbon prices from $8.50 to $2 per kilogram shows that positive NPV and IRRs above 10% are achievable across a large portion of that range. The higher the conversion and the stronger the carbon market, the better the economics, but the project doesn't need perfect conditions to be viable. This shows that you don't have to sacrifice returns to decarbonize. With the right process design, the carbon co-product pays for the transition. The results show that the proposed system can maintain grain drying functionality while introducing solid carbon as a co-product and creating a pathway for emissions reduction. This demonstrates that Aspen Plus can be used not only to simulate a process, but to evaluate feasibility, guide process redesign, and support innovation in thermal systems. This project shows that the path to low carbon agriculture doesn't have to run through expensive new infrastructure. Sometimes it runs through a smarter use of the fuel we're already burning. Thank you.